Okay, so for problem 49, they want the area between these things. So this is a line right here, and this is a parabola. So let's see, just based off of sort of insights pertaining to past math courses, meaning prior knowledge of how this stuff works, I think it should be clear to everyone that the line looks something like that. And hopefully it's clear the parabola looks something like this. And what we're looking for, therefore, is the area of this yellow shaded region here. Now, I can see that it's going to be a matter of finding clear the area between the green line and this parabola. I'm going to suggest getting clear on these points of intersection. That is going to be fairly easy because x equals 2y squared. So that means we can mess with this formula and say that 2y squared plus y equals 1, and therefore 2y squared minus 1 equals 0. We can then factor it, and we'd have 2y, we'd have y, I believe it would be plus 1 and minus 1 here. So therefore we can see that y would certainly be negative 1, that's one of them, and then the other y would be 1/2. So we basically found the y coordinates for these points of intersection, and we could set up an integral where those y coordinates are presented in the bound, okay? So in the bound, so we're going to have 1/2 minus negative 1, and it's going to be the green line minus this parabola. That's what would give us that yellow shaded region. So in the case of the sideways kind of situation, you're going to want to go from right to left, okay? And similarly, with regards to the y values, the bounds, you're going to go from greatest to smallest, all right? So moving from right to left means it's going to be the line equation minus the parabola equation, but we want that line equation to be in terms of y. So what that means is we have to take this equation here and solve for x. So it's going to be 1 minus y. So really what we're dealing with is 1 minus y minus the parabola equation that is also in terms of y. So that's going to become 2y squared. And that's going to be all with respect to y. And that should do it. Let's perform the integral now. It would be certainly y minus y squared over 2 minus 2y to the third over 3 with this 1/2 negative 1. And then we would have something minus something squared over 2 minus 2 times something cubed over 3. And we would be subtracting an entire quantity of the exact same structure. Something minus something squared over 2 minus 2 times something cubed over 3. And according to the bounds, the numbers that we are plugging in would be 1/2 and negative 1. So I'm going to just fill that in. 1/2 and eventually negative 1. So we have 1/2. 1/2 squared is 1/4 over 2 would be 1/8. 1/2 cubed is 1/8. 1/8 over 3 is 1 over 24. Negative 2 over 24 is negative 1/12. And we will be subtracting the entire quantity of this stuff, so we are looking at negative 1. 1 squared is, of course, 1, so it's going to be negative 1 minus 1/2. Negative 1 cubed is negative 1, so that's going to become a negative 2 times a negative 1, which is a positive 2, so that is going to become plus 2/3. At that point, I think we can go ahead and distribute the negative. Let's rewrite this part. It's going to be plus 1 plus 1/2 minus 2/3. So I believe the best common denominator for these fractions would be 24. So I'm going to put a 24 down there. Looking at the numerators, it would be 12 minus 3 minus 2 plus 24 plus 12 minus 16. That would simplify into certainly 24 down below. The 12 minus 3 is 9, minus 2 is 7, plus 24 is 31, plus 12 is 43, minus 16 is 27. So we have 27 over 24, both divisible by 3, so that would be 9 over 8, and that is the answer to that one. So it did require an insight to understand that we're dealing certainly with the area between two functions, or we could say curves, even though the line really isn't a curve. It does require us to realize it's sort of a sideways scenario. That means we're going to have to subtract the leftmost parabola from the rightmost green line. What you don't want to be doing is subtracting a function from itself. So you might be wondering, well, why didn't we just go straight down? Well, first of all, because there would have been this region where it would have been the parabola subtracting itself. So we want to avoid that. We want one function on the so-called top and the other function on the so-called bottom if we're going to be doing that subtraction. Or maybe in this case, I should really say, we're going to want one, in the case of a sideways scenario, we want one function to the right and the other function to the left to avoid that situation where we're subtracting a function from itself, okay? So hopefully that makes sense. Had this been something like that, where it's like area between the thing, well, then it would have been two x values here, and this whole thing would have been x stuff minus, it would have been the line minus the parabola in terms of x. All right, and that would have been dx, okay? In the case of the sideways situation, the bounds correspond with the y coordinates as opposed to the x coordinates, and the functions in the integral need to be in terms of y, okay, with respect to y and all that good stuff. So that is important to understand for that one. Okay, give a sketch of the region between the curves y equals cosine x, yada, yada, yada. Find the area of the region. Okay, so first we need to give a sketch, and it's from 3 pi over 2. Okay. Well, the amplitude of this is 1. So this curve gets as high as +1 and as low as -1. The amplitude here is also 1, but there's a vertical shift upward 1 unit, so the highest y value present here is going to be +2. So I'm going to say let's create a graph that kind of looks like this to make it sort of even looking. We'll do this. I'm a fan of sort of putting 2 pi here, at least for now. Pi is right in between. You clearly have pi over 2, and you clearly have 3 pi over 2 here. It turns out we're only really interested in this yellow region according to the information right here. Nonetheless, I'm still going to graph both things just across the 2 pi domain because that's sort of a little bit more what I'm used to, and then we could make any edits after that. So the cosine one is in green. Cosine would start here, kind of looks like a vase. It goes down, it reaches a minimum there, and then it cuts up like that, and then it goes back up to 1. With regards to sine of x, typically it starts here and it goes like that. However, it's going to be shifted up 1. Now I'm going to draw a rough draft sketch nonetheless in blue. Typically it would look something along these lines, and then it would go here, and the values of interest are right here, this red point, this red point, this red point, and this red point. And in order to take into account that vertical shift of 1, we're just going to move those red points up. So I'm actually going to draw it here like that. We're going to move each red point up 1, and then it ends up being like that. So we have our sine function that looks like this. Now, time to erase stuff that we don't need. First of all, we certainly do not need this rough draft 1 right here. We don't need that. And also, we don't need any of this stuff over here either, do we? Because the space we're interested in is just from 0 to 3 pi over 2. So we've satisfied their first thing, where they ask us to simply sketch the region, and we just did. Now I'm going to maybe color it actually. We'll color it in purple. So that's the region. Then they want us to find the area of the region. Well, I think we can clearly see it's going to be the sine minus the cosine, and it's going to be the integral of that. And we already have our bounds. The bounds would be 0 and 3 pi over 2. So this one turns out to be not too bad, as long as you know the sort of graph of sine and cosine functions. So we're going to have 3 pi over 2 up top. We're going to have 0 down below. We will have the sine function up top, so it's sine of x plus 1, and we're going to be subtracting the cosine of x, and that will be with respect to x. And I think relying on the trig reference guide would be good. So we can clearly see that the integral is going to be, well, the integral of sine of x is over here. That's negative cosine of x. It's going to be plus 1 because the integral of this 1 is going to be, actually x, I should say, plus x, pardon me. Then we're going to be subtracting the integral of cosine x. Now, the integral of cosine x is just sine x. We're going to be subtracting sine x. And we have 3 pi over 2 here and 0 here. Now, I think we all understand this is going to be a matter of substituting 3 pi over 2 and 0 in. So it's going to be negative cosine of something plus something minus sine something minus the entire quantity of the exact same structure. So that's going to be minus cosine of something plus something minus sine of something. So as far as those somethings go, the somethings are going to be 3 pi over 2, at least in the beginning, 3 pi over 2, 3 pi over 2, and then 0. 0, 0. Okay, looking at the unit circle, I think this is going to be helpful. Okay, I think that's going to be helpful. So, negative cosine of 3 pi over 2. Well, cosine of 3 pi over 2 is 0. So that's going to be just a 0. Plus 3 pi over 2. That's literally going to be plus 3 pi over 2. We have minus sine of 3 pi over 2. Well, sine of 3 pi over 2 is negative 1. So that's going to become negative 1, minus negative 1, aka plus 1. And then we're going to be subtracting a quantity. Now, what is the quantity? Well, it's going to be negative cosine of 0. Well, cosine of 0 is 1, and negative cosine of 0 would therefore be negative 1. Then we have plus 0, which I do not have to write, minus sine of 0. Sine of 0 is 0, so I do not have to write that either. Okay, don't have to write that either. So we have all this, and pretty simple to simplify. Yeah, that's plus, right? So it's going to become 3 pi over 2 plus 2. So that's the answer. There's always a chance it might be written as 3 pi plus 4 over 2, okay? Because that is the same. 4 over 2 is just 2. 3 pi over 2 over 2 is just that. So that's the answer to that one. All right, so problem number 51. The region enclosed by the curves, blah, 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 rotated around the line y equals 1. Find the volume of the resulting solid. Well, the purple, or the blue one, I should say, purple, blue one, looks like this. And this one, which we will make a green one, most definitely looks like this, like that. And it's going to be rotated about the line y equals 1. Well, let's find out where they intersect. Let's do that first. So we could set them equal to each other, and we would quickly see that x equals x to the, we'd have to square both sides. So x is going to equal x to the 6th, and subtracting x from both sides gives us this. And factoring out an x gives us x to the 5th minus 1 equals 0. And at that point, I think it's pretty clear x would be 0, which makes sense. And then the other x, if you set this equal to 0, you would quickly realize that x is equal to 1. So that's the case for sure. It's also true that, let's see, the y coordinates of this point would be 0, and I get that after plugging this 0 into really either of the two. And then when you plug x equals 1 into either of the two, you would get y equals 1. So it looks like these points are most definitely 0, 0, 0, 0, and 1, 1. And we are sort of analyzing the space in between, which is this region here. Let's see, this region here. Now that apparently is going to be rotated around y equals 1. And I'm also going to make a mental note that the strip would be like that. So that's going to be a washer method. Now you might be wondering how I know that. So I decided to make a little chart here that can help with understanding whether or not you're dealing with a washer method or not. And I got this inspiration from another YouTube channel, actually, and I want to plug her channel. If you check out Ashley the Math Tutor, I will post a link to her video in the description below because that was the inspiration for this. So I would suggest following her. I've yet to see somebody actually present a flowchart, and I think that that's probably the best way to go. She also sort of summed up these formulas as well, which we're going to get to in a moment. But one thing to note before we even look at the flowchart, if you see this strip is vertical and the axis of rotation is horizontal, okay? So that strip is perpendicular to the axis of rotation. So the thought process you want to go through in order to figure out what kind of method to use is this. If the strip is vertical or parallel, well, it's perpendicular. It's perpendicular or parallel. It's perpendicular, meaning is it perpendicular or parallel to the axis of rotation? The dotted line is the axis of rotation. The strip that connects one function to the other is perpendicular to that axis of rotation. And the next question is, does the strip sit on the rotating axis? In other words, is it touching the rotating axis? Well, it's not. It's spaced away from the rotating axis. So the answer is no, so therefore we're going to use the washer method. So for my student at home, first of all, you might want to watch Ashley the Math Tutor's video, because it's a great video, or simply screenshot my version of her flow chart as well, and just maybe crop it so that you have it in your phone or whatever. So the next question is, okay, fine, we're going to be using the washer method. Well, here it is right here. So let's do it. Let's go ahead and use it. So to use the washer method, which is right here, I'm actually going to say let's take this pi and put it on the outside. So it's going to be pi on the outside. Let me actually get rid of that. So we're going to have pi, and it's going to be the big radius squared minus the small radius squared. But then the question is, well, what is the big radius? Well, the big radius is the distance between the axis of rotation and the function that's further away from it. In this case, it's the blue one, okay? So the distance between this axis of rotation and the blue function, well, that's going to be 1 minus the blue function. That's the distance, okay? It's 1 minus the blue function. Now, the blue function is x cubed. So the big radius is 1 minus x cubed. Then the small radius, which goes here, is going to be 1 minus the green function, the closer function. So if you look closely, the axis of rotation is here. We're going to be subtracting this green smaller function, and the green smaller function in this case is radical x. So that's going to be 1 minus radical x. So we will have to FOIL these or rely on a memorized pattern when it comes to multiplying these binomials times themselves. So one way or the other, let's go ahead and do it. Also, let's remember, I should have put this before, it's going to be 1 and 0. Those, by the way, are the x coordinates that we're going between, all right? The larger x coordinate is 1, and the smaller x coordinate is 0. It also happens to match the y coordinates, but it's in reality the x coordinates that we're working with there. So then after sort of working out the blue one, it's going to be 1 minus 2x cubed plus x to the 6th. And then we're going to be subtracting this entire yellow one. It's going to be minus, and I'll keep it in brackets. Well, I should make this blue. So it would be 1 minus 2 radical x plus x. All right, now in case that's not clear, then go ahead and pause the video and confirm for yourself. Okay, so we still have the dx over here. Now let's be clear about what's happening here. It's going to be a minus 1 plus a 2 radical x minus x after distributing that negative. And I think we could all see that the 1's are going to cancel. Now, On the next line, we still have the pi. We have 1 and 0. We have 1 and 0. We also have, let's see, negative 2x cubed plus x to the 6th plus 2, I'm going to call that x to the 1/2 minus x, and that's all dx, and that's something we could definitely take the integral of. So let's do it. We're going to have pi on the outside. We're going to have negative 2x to the 4 over 4 plus x to the 7 over 7 plus 2x to the 3/2 times, we could say times 2/3. I'll put it over here. Minus x squared over 2. And we would have our 1 and our 0 there. And at this point, we can simplify some things. We've got a 1 and a 2. The 2 times 2 over 3 is going to become 4 over 3. I'm going to say let's go ahead and get that over with. It's just going to be 4 over 3. So 4 over 3. Okay, well, at this point we can substitute stuff in. That would be pi times negative something to the 4th over 2 plus something to the 7th over 7 plus 4/3 of something to the 3/2 minus something squared over 2. Now typically we would subtract the exact same structure such that we could plug 0 into the structure over here, because 1's going to go into this one. We're going to plug 1 in here, here, and here, and we're going to be subtracting the same structure only with 0 plugged in here, here, and here. But that would result in a 0. So I'm going to say let's save ourselves the work and not even bother with that, because when you subtract 0, you end up with just the thing that you started with. So this would be the thing we started with, which is to substitute 1 in there. So, yeah, let's take a look. Well, it would be definitely pi times negative 1/2 plus 1/7 plus 4 over 3, minus 1/2. And a good common denominator for all of that, in my opinion, would be, well, 21 times 2. What's that? 42. So if we were to treat 42 as the common denominator, it would be this fraction with 42 on the bottom. And on top, we would have negative 21 plus 6 plus 42 divided by 3. What is that? That's going to be 14. And then 14 times 4 is, well, that's 42 plus 14. That's going to be 56. And then we're going to have minus 21. So just use, your sort of basic math skills to turn these into fractions. We're going to add them all together. You're going to get the common denominator. And of course, we have to add these or combine all these up top. And that's going to be, well, that is definitely 62 minus really 42. And 62 minus 42 is 20. So that's going to become 20 over 42 pi, which reduces to 10 over 21 pi. So, I mean, I kind of did a whole bunch of that in my head towards the end with this whole section, but just know that I did nothing other than finding a common denominator, and I added everything together, and I got 10 over 21 pi. That is the answer to that one. Okay, the base of a solid S in the parabolic region, yada, yada, yada. Cross sections perpendicular to the y-axis are equilateral triangles.
So if we were to sort of look at the graph, we definitely have a parabola here and a that would be a horizontal line there. So the horizontal line cuts through the y value of 1, and the parabola looks like that. And also, well, therefore, we're dealing with this shaded region here, but we're not just dealing with the area of the shaded region, we're dealing with equilateral triangles such that the cross sections are perpendicular to the y-axis. Okay, so here would be an example of such a cross section, which you could see as the base of one of the equilateral triangles. You can imagine the equilateral triangle kind of stands up in 3 dimensions like that, but we're going to stick with this sort of overhead view, which is like 2-dimensional. Okay, so that's the reality of what's happening, at least from the overhead shot. Now, whenever the cross section is perpendicular to the y-axis, what that means is we're going to be setting up an integral where the area function needs to be in terms of y. Okay, it needs to be in terms of y. And when I say area function, I mean the area of the equilateral triangle in this case. Okay, and that once again is true because the cross section is perpendicular to the y-axis, and therefore it's going to be the area function in terms of y dy. And it's also going to be such that you have the change in values between the y values. So we already know this is going to go from the y value of 1 to the y value of 0. In other words, it starts up here and then it goes down, right? Because this sort of red shaded region is the region that the equilateral triangles are going to be inside, okay? So it goes from the y value of 1 to the y value of 0. Notice how we're disregarding the x coordinates here. They're kind of irrelevant, as it turns out, at least for the bounds, okay? Now, the question, though, is what is the area of an equilateral triangle in terms of y? Well, let's just take a look at any old equilateral triangle, and let's just get clear that the base in this case, since it's positioned like this and it's symmetrical, in the first and second quadrant there, symmetrical about the y-axis, then this entire base is going to be whatever this x is plus whatever this x is, okay? So the base is going to be 2 times x. And of course, this would be 2x, this would be 2x as well. And if we were to drop the altitude down or the height down, well, that would make this part x, okay? That would make this green part x because it would be half of 2x. Now, some of you may recall that whenever you sort of cut an equilateral triangle in half like this, you end up with 30, 60, 90 triangles. This is 30 degrees, this is 60 degrees, and this is 90 degrees. And 30, 60, 90 triangles are such that the long leg, in this case the altitude, is going to be x root 3. Okay? The altitude, which I'll actually make in red here, is going to be x root 3. So in other words, the altitude, this long leg of a 30, 60, 90 triangle, is going to is half, or actually I should say, is whatever the short green leg is times root 3, okay? Let's just focus only on this little triangle here, not the whole thing, okay? We're going to focus only on this little triangle. 30, 60, 90 triangles are such that the long leg is whatever the short leg was times root 3, so it's going to be x root 3. So, why am I saying all that? Well, the area of any triangle is 1/2 base times height. So what we're learning is the area of this triangle, since it has a base of 2x, is going to be 2x times the height. Well, what's the height? The height is x root 3. I think we would all agree the 2's would cancel, and we would end up with x squared root 3. Now that is the area function, however, it's in terms of x. So we need to find somewhere in the problem where x is related to y. Well, that would be found here. Y is greater than or equal to x squared. So y is equal to x squared. Okay, you could say that y is equal to x squared. So therefore, anytime you see an x squared, you could replace it with a y. So that's a place where we have just found we can relate x to y. Apparently, x squared equals y. So there it is, y root 3. So the area of this triangle that has a base of 2x is actually equal to y root 3, if we were to put it in terms of y. Okay, so that's quite a mission, right? You had to kind of just work off of this diagram, simplify it down. So it's like, okay, I guess the area is x squared root 3, but you need to put it in terms of y. So you're like, okay, well, does x relate to y anywhere in this problem? Well, absolutely. X squared equals y, apparently. So here it is. So that's the area function that we're going to be integrating. And then we're going to be home free. Okay, so kind of an interesting process. I would say this stuff definitely takes practice for sure. But let's do it. We've got y root 3 dy. The root 3 is just a constant, so that could actually go outside. I'm going to go ahead and do that now. I'll just rewrite it, actually. So we have root 3 on the outside. We've got 1 and 0. We've got y dy. Okay. So then it's root 3 times y squared over 2. And we have 1 and 0. Now, it would be a matter of substituting 0 into that and then subtracting it. But if we were to substitute 0 in for that, it would just become 0. So we could actually ignore that part. All we really have to do here is to substitute 1 in for y at this point. So that's going to be 1 squared over 2. And that is going to result in radical 3 over 2. And that is the answer. Okay, so these are a kind of problem that will require practice. The big picture is that if the cross section's perpendicular to the y-axis, then you're going to want to use the area function in terms of y. If the cross section was perpendicular to the x-axis, then you're going to want the area function in terms of x dx, and you're going to have the change in x in the bounds as well. Okay. And then it's going to be a matter of figuring out, well, what's the area in general of the shape? What's the area of the shape, in this case, equilateral triangle, as it relates to the cross sections and as it relates to the xy coordinate plane? And then set that up, find the area, make sure it's in terms of the variable you want, and then plug it right here, and then just perform the integral, and then you're good to go. So I hope that is helpful, and I will talk to you all later. Good job. Take it easy.